You turn the handle, step back, and wait. Waiting for the shower to actually get hot is a minor daily annoyance for most of us. But behind the drywall, heating that water accounts for 12 to 18% of your home's total energy use. That delay before the hot water arrives is the symptom of a deliberate engineering decision. The pipes hidden in your walls and ceilings are built far wider than necessary. The layout of these pipes, valves, and heaters is called a premise plumbing system, and the foundational rules for how wide to build those pipes haven't been updated since the 1920s and 40s. Specifically, engineers use a mathematical calculation known as the Hunter curve to estimate what's called probable simultaneous demand. This math assumes your plumbing needs to be wide enough to handle a scenario where every single fixture in the building is turned on at the exact same time. 80 years ago, sizing pipes for absolute maximum capacity was a practical way to prevent drops in water pressure. Today, that outdated math is actively sabotaging the efficiency and safety of modern buildings. This graphic shows how modern conservation strategies have altered residential water use. By switching to low-flow shower heads and dual-flush toilets, we've successfully reduced household water consumption by up to 20%. But there is a glaring mismatch in the design. We reduced the volume of water trickling out of the taps, yet building codes still dictate that pipe diameters remain built for 1940s level surges. Sending a tiny volume of water through a wide-bore pipe leads to a problem engineers call water age. The flow velocity drops, the water pools, and it eventually comes to a complete standstill. During these long periods of stagnation, the chemistry inside the pipe breaks down. Protective chlorine disinfectants quickly decay away, while modern plastic piping begins leaching organic carbon directly into the sitting water. This creates a lukewarm, stagnant, and carbon-rich environment. It is the perfect breeding ground for opportunistic premise plumbing pathogens, dangerous bacteria like Legionella that naturally thrive and multiply in these exact conditions. Because we treated water conservation as an isolated add-on, we lowered our usage but accidentally turned the wide-diameter pipes in our walls into toxic bacterial ecosystems. This diagram maps the water-energy nexus. Cold water flows in blue, but notice the red thermal lines traveling from the water heater. Oversized pipes hold large volumes of sitting hot water, acting like hidden radiators constantly leaking heat into the walls. The thermal waste is substantial. Because of oversized layouts, between 13 and 29% of the energy used to heat domestic water is entirely lost before a single drop reaches the tap. To keep bacteria from growing in these long cooling loops, building managers often resort to blasting the water with extreme heat to sterilize the system, which burns through even more energy. As long as we rely on 1940s pipe sizing, homeowners are trapped in a harsh paradox: lower the water temperature and risk bacterial infection, or raise the temperature and bleed money. Reactive fixes, like periodically flushing the lines or running sudden heat shocks, are highly temporary. To solve this, the foundational design of the entire plumbing system has to change. This conceptual model visualizes a new engineering philosophy called integrated design. Instead of calculating pipe width, energy use, and water quality as isolated problems, engineers now treat them as a single cohesive unit. At the core of this approach is stochastic modeling. This replaces the 1940s Hunter curve by using high-resolution data to accurately predict real human behavior, allowing engineers to design much narrower pipes that easily handle varied, unpredictable bursts of use. This schematic illustrates how those right-sized pipes are then paired with smart technology. By installing demand-controlled recirculation pumps linked to occupancy sensors, the system only moves hot water when someone actually enters a bathroom. The final hardware upgrade is the heat pump water heater. Instead of burning gas or using electrical resistance, these pull ambient heat directly from the surrounding air, making them up to 3 times more efficient than traditional heaters. This transition treats premise plumbing as a living ecosystem integrated into our architecture. By abandoning a century-old math error and shrinking our pipes, we gain a direct path to cutting our carbon footprint, lowering utility bills,